start by considering that nx sine of theta x is supposed to be always equal to a constant, and that's Snell's law. And we can sort of set this equal to n0 sine of theta 0, or rather we could call it just the initial angle here. And this will sort of help us with the rest of the problem. And we're given an x as the part of the question, so we have qd minus x plus 1. And when we set n0, so x equals 0, and we're just going to get something like qd plus 1. So that's pretty cool. That means that we can plug it right back into the solution, and we'll get something like, let's plug everything in all at once. We got q d minus x plus 1 is going to be nx. Then we have sine of this theta x here, and it's kind of what we want to solve for. Okay, and then that's going to be equal to n0, which is qd plus 1, and then we have the sine of its first angle. And so we can rearrange this equation a little bit and sort of move this down to the bottom, and we can get our answer for sine of theta. So that's pretty nice. Now, if we're considering small angles, just realize that tangent of theta is approximately equal to the sine of theta. And we do know that tangent of theta is supposed to be equal to dy over dx. Therefore, we can say that dy equals dx tangent of theta. Of course, we can approximate that as being dx sine of theta. So now what we can do is we can just go ahead and say that we can put maybe a dy is going to be equal to dx times the sine of theta, which is all this stuff over here. Now we've given ourselves a nice little integral to solve. Now we're going to integrate this from 0 to d. X goes from 0 to d. In fact, let's label these as x goes from 0 to d. Because in order to solve this integral, we need to use a u-sub. I mean, technically we don't have to, but it'll be a little bit easier and things will just make a little bit more sense. So let's just do that. We're going to use this bottom part as the u-sub portion. We're just going to say qd, let's expand it, qx plus 1. That's what u is. It means that we can get a du being equal to just negative q dx. Not too bad here. And then once we plug in x equals 0 and x equals d, then we can set some new limits. Just go ahead and just call it y, I suppose. But y is going to be equal to the integral here. So when x equals 0, then we get qd plus 1. And when x equals d, we just get 1. And then we're going to leave qd plus 1 on top. And the sine of theta as well. So that doesn't change on the top. And on the bottom, we're just going to put u. And then dx is essentially du divided by negative q. Alright, so this now becomes pretty easy because this stuff here on top is now a function of u, so it's a constant, so we're going to pull that out. Same thing with the bottom part over here, it's just negative q, we're going to pull that out. So we kind of put this in the beginning. We're constant. The negative sign, we can even get rid of that and flip the two integration limits. So we'll just put the integration limits backwards. 1 qd plus 1. And then the last part is just du over u. And that's just ln of u. So we have our answer, essentially. This over here And then we're just going to get ln of qb plus 1 minus ln1. And of course, the ln of 1 is just 0, so that could just go away. And so we're left with the answer, I suppose, right here. It's pretty nice for what y is equal to this. Yes, this is just kind of an interesting solution to this problem.